Welcome, and thank you for joining this session on understanding motion through the SUVAT equations. Today, we'll explore a strategic toolkit designed to make sense of uniform acceleration, breaking down key concepts in a clear and practical way to help you confidently approach related problems and applications. Let's dive in and start decoding motion together. Let's focus on what uniformly accelerated motion really means. It's about objects moving in a straight line while their acceleration stays constant, like a car slowing down steadily, an object falling freely under gravity, or a dragster speeding up at a constant rate. This means the change in velocity happens evenly over time. On the other hand, it's not about situations where acceleration changes unpredictably, like when a car weaves through traffic or a pendulum swings back and forth, because in those cases, the acceleration keeps fluctuating and isn't steady. Understanding this distinction helps us apply the right tools to analyze motion accurately. Now, let's look at the key variables we use to describe motion, often called SUVAT. Each letter stands for an important part of an object's journey. S is displacement, which is simply how far the object moves from its starting point to its end point. U is the initial velocity, or how fast the object is moving right at the start. V is the final velocity, or how fast it's moving at the end of the time period we're considering. A stands for acceleration, which is the rate at which the object's velocity changes over time. And finally, T is time, which tells us how long the motion takes place. By understanding these 5 variables, we can capture the complete picture of an object's motion. Here are 4 key equations that form the foundation for solving problems involving velocity, acceleration, time, and displacement. Each one connects these variables differently, so if you know any 3, you can use the appropriate formula to find the missing one. For example, the first equation relates final velocity to initial velocity, acceleration, and time. The second calculates displacement using the average of initial and final velocity multiplied by time. The third expresses displacement in terms of initial velocity, time, and acceleration squared over time squared. Lastly, the fourth connects the squares of final and initial velocities to acceleration and displacement. Understanding these will make it easier to analyze motion and solve related physics problems efficiently. Let's look at a clear 3-step process to tackle problems efficiently. First, start by setting up your strategy. This means drawing a simple sketch to visualize the problem and choosing a positive direction. It's important to list what you already know and what you need to find out, then pick the single equation that involves exactly those variables. Next, move to the execution phase by doing the actual calculations. Substitute your known values carefully into the equation, watching your positive and negative signs, and work through to get your numerical answer. Finally, step back and critically check your result. Ask yourself if the answer makes physical sense by reviewing the units, the size of the number, and whether the sign aligns with what's realistic. This approach helps ensure your solution is both mathematically correct and physically meaningful. Now let's look closely at how the plane slows down after landing. We know it starts at 70 meters per second and slows down at a constant rate for 40 seconds. Since it's decelerating, the acceleration is negative, pushing back against the forward motion. Our main goal is to find the final velocity after this 40-second period. We'll use the initial speed, the negative acceleration, and the time to work this out step by step. This sets up a clear path to calculate the exact speed when it finishes slowing down. Here, we focus on finding the final velocity using the equation v equals u plus at, where we already know the initial velocity u, acceleration a, and time t. Plugging in the numbers, we start with 70.0 meters per second for u, apply the acceleration of negative 1.50 meters per second squared over 40 seconds, which subtracts 60 from the initial velocity, giving us a final velocity of 10.0 meters per second. This result makes physical sense because the final velocity is significantly less than the initial velocity, which aligns with what we expect when a plane is landing. It slows down safely but still moves forward toward the terminal. The positive final velocity confirms the plane's controlled deceleration during the landing phase. Let's move on to the next part, where we focus on an accelerating dragster starting from rest. The dragster accelerates at 26.0 meters per second squared over a time period of 5.56 seconds, and we want to find out how far it travels during this time. To do this, we establish our starting point as 0, meaning the initial displacement is 0, and both velocity and acceleration are positive in this direction. We know that the initial velocity is 0 because it starts from rest. The acceleration is 26.0 meters per second squared, and the time is 5.56 seconds. Our goal here is to calculate the displacement, which is the distance the dragster covers during this acceleration phase. Let's continue by looking at the next part of the problem. The key here is to focus on the distance the car travels as it stops, using the information we have about the initial speed and the deceleration. Since the time to stop is not given and not needed, we'll apply the relevant equations that bypass time. This approach will allow us to find the stopping distance directly, making the solution straightforward and efficient. Now that we've done the calculation, it's important to consider whether the stopping distance we found makes sense in a real-world context. A distance of about 64 meters is quite reasonable for a heavy vehicle traveling at highway speeds, which reassures us that our result is practical. This also shows the effectiveness of the method we used. It allowed us to solve a fairly complex motion problem accurately without needing to rely on direct timing measurements, like using a stopwatch. This approach is not only efficient, but also powerful for understanding motion in similar situations. To wrap up, let's review the SUVA playbook in one clear overview. We start with the language, defining the key terms: displacement, initial velocity, final velocity, acceleration, and time. Then, the toolkit consists of 4 main equations that link these variables. Each equation is designed to help solve different parts of a motion problem depending on what is known or unknown. Finally, the strategy emphasizes a step-by-step approach. First, sketch the scenario and identify what you know and what you need to find. Next, substitute the values into the right equation and solve. And lastly, check the solution against physical reality to make sure it makes sense. Keeping this approach in mind helps simplify complex motion problems and ensure accuracy throughout.